Everyone, this is Maxwell from Southeast University, Nanjing, China. Our work focuses on object detection of sonar image. Currently, the volume of noise image is scarce and the noise perturbation makes the detector deteriorate. In this paper, we propose an adversarial method to generalize the object detector. Specifically, we propose a sideways network which is named noise adversarial network. It generates adversarial examples with random noise which follows Rayleigh distribution. In addition, we design an auxiliary component called noise block to further improve the noise robustness. The previous work usually focused on optical images. In the meanwhile, they were always designed with man-made features which shows low generalization and restrict the additional noise into a limited space. In this paper, we propose a generalization method based on faster Tseng. We assign the noise adversarial network following our polling layer. In this component, we use a convolutional layer with two fully connected layers, which predict wide range of noise for each feature map to simulate the sea reverberation. Then the noise is introduced into the original feature maps to generate adversarial examples. In the meanwhile, we design noise block to induce speckle noise in the upstream layers to provide priori knowledge for noise adversarial network. The noise block introduces speckle noise into a feature map with low semantic but high resolution. We generally treat adversarial network and noise block with three kinds of loss functions. To validate our method, we gathered a sonar image dataset with use random cropping to extend the original dataset for data augmentation. The result on our dataset shows that our method outperforms the baseline as well as other two adversarial training methods. We also conduct an experiment of ablation study with noise block. It is shown that the result improved by inserting the noise block into the upstream layers. In the meanwhile, it is shown that with the effect of NB, NAN can predict the speckle noise perturbation in a different domain according to structures of backbones. We also demonstrate that with the assistance of noise block, the noise adversarial network achieves high noise robustness. It overcomes the noise attack with all intensities. The error analysis shows that the NAN and NB extensively eliminates the false positive of misaligned localization and misclassification. Finally, we proved the universality of our model. We use it on Pascal VOC 2007 with both Gaussian and Rayleigh noise attack into the test set. We achieved 2.4% higher performance than baseline. It also illustrates the noise robustness of Gaussian and Rayleigh noise attack. And there are some results of original and noise datasets. So if you have any questions, please come to see our poster, and thank you for all your listening.
Hi everyone, so today I will be presenting on behalf of the authors on their work on active learning and domain adaptation. Typical unsupervised domain adaptation has labeled data from the source domain and unlabeled data from the target domain. The goal is to perform well on the target domain. However, if we have a few labeled data on the target domain, the model can perform better than using UDA techniques alone. This is also a more realistic scenario where we have a budget to limit label images in the target domain. In this work, we try to answer two questions. First, how should we train the model given few labeled target? We use domain adversarial training where a discriminator is trained to predict whether the data is from the source or target domain. Second, how should we select images from target domain to label? We use importance weights, which can be obtained from the discriminator. The importance weights for domain adaptation has two parts. The first one is called importance, which is the ratio of density between source and target samples. The second one is empirical risk. Since we do not know the label before selecting the sample, we can only estimate it. We first obtain the importance from the predictions of the discriminator. The final score is calculated by the product of the two terms. First, the importance measures the diversity of the samples, and second, the uncertainty put more weights on hard examples. Overall, we propose an iterative method. First, we train an adversarial model given labeled source and unlabeled target. Second, we use the importance weight to select images from the target domain for annotation. Then, we train another adversarial model with the union of label source and label target data. We iterate this procedure during active learning. Here, we show our results of object detection adapting from kitty to cityscapes data set. When we have budget of less than 1,000 label images, our AADA outperforms other active learning method and other training method. In conclusion, we are the first to investigate active learning and domain adaptation using deep networks. We use adversarial training for adapting model and importance weight for selecting samples to annotate. Our method shows improvements on classification and detection benchmarks. Thank you. And I will be presenting my own work in the following, so bear with me. So hi everyone, my name is Han Kai-Su, and I would like to present our work on progressive domain adaptation for object detection. For the object detection task, the main objective is to provide bounding boxes and category label to every object in the given scene. Modern state-of-the-art detection methods are based on deep learning models. These supervised models, however, usually has difficulties when applying to different scenes in the domain other than the source domain it is being trained on. A straightforward way to solve this issue is to collect new annotations in the unseen domain to retrain the detection model, but this would be labor-intensive and really costly. To get around this without annotations, there are domain adaptation methods that tries to align the two different domains, but these domains are often very different and thus exists a large domain gap that is hard to align. In our work, we present a progressive adaptation method to cross this big gap with a stepping stone in between. By utilizing CycleGAN, we map the source domain images to the target domain, producing a synthetic domain sitting in between the two domains. We then use the intermediate domain to first adapt from the source domain to the synthetic domain, focusing on aligning the appearance differences. Afterwards, we adapt from the synthetic domain to the target domain, focusing on the object variations in the two domains. Our method hence only needs two smaller adaptation steps to cross the big domain gap. Here's an overview of our adaptation network structure with a detection branch and another adaptation branch for aligning the two domains at the feature level with adversarial learning. Our objective function is the detection loss plus the discriminator loss. In the synthetic domain, we also found that the image quality varies in the generated images. As we can see on the right, there exist many artifacts, but the left ones do not. To prevent the model from being misled by the poor examples, we apply a weighted supervision to the detection loss in the final objective function. We utilize the discriminator score from trained CycleGAN model to provide higher score for better quality images and lower score for bad images, guiding the model to adapt using the better quality images. Finally, we show that our method can achieve state-of-the-art performance on several adaptation scenarios. First is cross-camera adaptation, where we have a 5% improvement. On the right, we can see that our adapted detector is able to detect the harder cases, like occluded vehicles and further away ones. Here are some additional results on the other two tasks. Finally, our main contributions are summarized as follows, and for more information, please stop by the poster or look at our code online. Thank you.
Hi, I will start my presentation with a question. Given the following three right turn events, how to quantify similarity between them? They all belong to the same class, yet they are different. My name is Ahmed Taha, and our paper extends standard architectures to quantify similarity between different objects. Standard architectures are powerful classification models. With ImageNet, they enable fine-tuning and feature extractions for new domains like medical images and videos. However, they cannot quantify similarity between objects within the same class. Our objective is improving feature embedding using a simple and efficient approach. Recent work recognized softmax's limitation. However, their proposed solution always assumed a fixed number of class representatives. This constraint requires a user input, which can be difficult, especially for imbalanced datasets. In this paper, we integrate triplet loss into standard architecture as a feature embedding regularizer. It promotes class compactness and inter-class margin maximization. It does not require a fixed number of class representatives. Our triplet loss integration is simple and straightforward. We simply add a single fully connected layer to create an embedding head. Triplet loss is applied to the new embedding head, while softmax is applied to the original classification head. Beyond improving classification performance, the standard architectures are now equipped with a retrieval capability. We can quantify similarity between objects. We quantitatively compare the classification and retrieval performance. The retrieval recall at 1 is very close to the classification performance, while recall at 4 outperforms the classification performance consistently. Our proposal adds a single fully connected layer to standard architecture. The network training time increases by just 2%. We hope this marginal cost will promote adaptation of the proposed two-head architecture. The proposed two-head architecture boosts classification performance and quantifies similarity between different objects. Our code is available on GitHub. Thank you.
Chen, I'm going to present our work, Overlap Sampler for Region-Based Object Detection. This is a collaboration work with Bing Luo, Qi Wu, Jia Chen, and Xue Zhenpeng. In recent years, we have witnessed the remarkable developments made by deep learning techniques for the object detection task, a fundamentally challenging problem of computer vision. To date, the top accuracy of object detection is that by region-based approaches. Despite the great successes made by them, there are still difficulties in training them, one of which is owing to the imbalance problem. During training, the number of negative examples is much larger than that of positive examples, which would make the training be dominated by huge negatives. To alleviate the imbalance, loss-based sampling methods are proposed. However, they would introduce considerable computational cost as the loss computation for each example is required. Fortunately, recent IOU-based sampling methods could match the accuracy of loss-based ones, but show much higher efficiency. However, existing IOU-based samplers ignore the overlaps among examples themselves. See this figure. The overlaps among examples themselves are quite different from the overlaps between ground truths and the examples. We find that this neglect may result in an incorrect NMS procedure. Our analysis shows that sampling and reweighting those highly overlapped examples have the higher upper bound in accuracy than other sampling strategies. To use the overlaps among examples during sampling, we propose overlap sampler that selects training examples according to the overlaps among them. We design a simple strategy to sample highly overlapped examples. Specifically, we introduce a probability sampling method to select those more confusing examples, that is, highly overlapped examples. Furthermore, we focus on high-quality positives by reweighting to achieve higher accuracy. On the challenging COCO benchmark, our overlap sampler yields 1.5 higher AP for faster RCNN. It is also effective for the instant segmentation task, with 0.8 mask AP improvement for mask RCNM. Here we show some quantitative results. Our code is released on this website. Thanks for your attention.
So good evening, my name is François Bremond. I'm presenting this work done with Usual, as is Drizzy Bertrand from Vedecom. It's about designing a pedestrian detector which is fast and accurate. Most of pedestrian detector are either two-stage, like faster as CNN, who are accurate but a little bit slow, or one stage, like SSD YOLO, who are faster but less accurate, and the goal is to get a good trade-off between both. So fast and accurate. So in this picture, you see the overall of the system. So on the bottom, we extract a good feature from early fusion from the different block of ResNet. Once we have these good features, we do a semantic pseudo-segmentation, so the heat map of the pedestrian. And thanks to that, we can select correct anchors. And then at the end, on the left, so we get the last stage as object detector and building box regression as usual. So the two main contributions are this semantic pseudo-segmentation. So for that, we get as input the feature map from the early fusion. So why pseudo-segmentation? Because we don't have a pixel ground truth, we have a bounding box ground truth. So what you can see on this picture, it's the heat map that we get, so it's not that accurate, but it gives a good understanding of where are the pedestrians. So to get this heat map, what we do, we have a 3 branch with a different level of dilation, and thanks to that, we can compute this heat map, where each pixel corresponds to the potential pixels pedestrian. And so this heat map helps us to select the anchors, so we don't select the anchors everywhere in the image, but only where there is this heat map. And so how we do this selection, so we have a 6 branch, 1 branch for each types of anchor with different aspect ratio, height and width. And for each branch, we have specific filters, and we do only classification and no regression, so this is very fast. On top of that, we are doing only on a few number of anchors, so that's why it's quite fast. So there's only classification. And when we select the best anchors thanks to this stage. And then, so we do feature pooling, and at the end, so this is like faster CNN, the last stage, where we do the bounding box classification and regression. And that's why we get a good result on the 2 data sets, City Person and Caltech Reasonable, where we get the best result, and we get accuracy below 3.9 and with a frame rate of 30 seconds. Thanks.
Good evening, everyone. My name is Yi-Hsuan. The title of my paper is Model Agnostic Metric for Their Short Learning. We'll give the talk following the 4 parts. Compared with traditional classification, ZSL, short for their short learning, doesn't share the label space for training and the label space for test. In this paper, we focus on the happiness problem, one of the challenges in ZSL. The happiness problem means some semantic vectors appear in top label list of many test samples, which is always harmful to ZSL. Recent work solves the happiness problem based on Euclidean metric. However, their conclusion depends on the specific model like ridge regression. For the greatest applicability, the motivation of this paper is to elevate the happiness problem without the limitation. The first contribution is that we draw the conclusion based on Cousin metric. A higher dimensional embedding space can better elevate the happiness problem. Compared with recent works, our conclusion can be generalized to different models. The second contribution is that we introduce a diversity-based regularizer, which encourages a smaller mean and a smaller variance of Cousin metric between pairwise embedded semantic vectors to enhance the model with greater discriminative ability. The backbone of our method includes three components: the semantic network, the visual projection, and the prediction classifier with the diversity-based regularizer. Here are the objective and the prediction functions used in our method. We provide the experimental results to verify our model-agnostic conclusion. We can observe that as the dimension of the Coulson metric space increases, the skewness value in different models decreases consistently, which means that the emergence of hubs is suppressed. In addition, we provide confusion metrics for our method with and without diversity. Most test samples are classified correctly by our method with diversity than without diversity, which means that the regularizer can enhance our model's discriminative ability. We also provide extended experiments to investigate the upper bound of a dimension in the metric space. Experimental results show that improvements are consistent across scale. Under the GZ setting, our method also achieves competitive performance. Thank you, that's all. If you have any question, please feel free to contact me.
Hi, I'm Matt William from Brigham Young University, and I worked in Dr. Farrell's lab on fine-grained visual characterization, which I'll refer to from here on as FGVC. So in FGVC, as with general image classification, data is often king. And as you can see in this map, this is a map of the United States on iNaturalist, and this is what happens if you search for birds. You'll get 2.25 million observations distributed across 1,000 species. Current data set collection tasks, like if I were to just want to build a bird data set from birds in the US, it's pretty easy. I can go on a site like iNaturalist, or I can go to Flickr or Google, pull images. Now this is the expensive part, labeling them. But after that time and that expense, it's still possible. If we look to an area though like the Amazon region, it's not quite so easy. 33,000 observations spread across 1,800 species means that, ignore the really expensive labeling part, we don't even have the data to pull online. If you wanted to build a bird data set that includes all these different species, you need to send a researcher down to the field to collect those images. Now if you notice here, one key idea that we had is that not all images are equally hard to classify. In the Caltech birds data set, that green violeteer on top is the only green and blue bird in the whole set. If you give the classifier you have just 5 images of that to train on, no matter what else is in the set, it'll get all the green violeteers right every time. So we took that kind of basic idea and thought, you know, not everything is clear-cut as the green violeteer and this common and elegant tern, but we do have this notion of maybe classes that we need more images of and classes we might need less images of. So if you took some initial data set like the one pictured here, 5 images per class, and you want to know which ones were the hard and which one were the easy, our idea was, and what we do in this paper is we take cross-site validation. We would take 5 different train sets, 5 different test sets, and we would compute different metrics on it. We would take the accuracy, we would take the loss, we would take the KL divergence, and from that we would choose whichever ones appeared by the given metrics were the hardest classes, and we would just feed them more images. And the results show that using a metric to do this, like using the best ones that we had were accuracy or the cross-entropy loss associated with the instances in the class, if you use that as your motivating factor for adding those images instead of just adding them to classes at random, you would find higher performance. One thing to notice is that in pretty much every case when you use a metric or when you try to find a way to determine which images are hard and which ones are easy, you'll end up with higher performance. Though there are some cases for the for the smaller jumps where that's not the case. Our key contributions are just a methodology for adaptively building data sets. And come see us at poster 38 if you're interested in hearing a little bit more.
Hi, my name is Ephraim Lowe, and my co-author is Johanna Cole, and we work for North Point Defense. And today we're going to be presenting our paper on Internet of Things discovery using deep neural networks. So Internet of Things, or IoT, is a rapidly growing network of devices with a broad set of consumer to commercial applications, with over 200 billion devices scheduled to be projected to be installed by 2020. And with the ubiquity of such devices, it's going to be hard to catalog all these. So these devices communicate using relatively narrowband intermittent transmissions with flexible transmission frequencies. So that precludes using commercial hardware solutions for RF sniffing, as they are often limited to predetermined frequencies. So for more generalized discovery, an analyst manually scans the RF using a digital waterfall display of the spectrum as seen here, visually identifying the signals of interest. And that's tedious and inefficient. So we focus our efforts on a class of signals that employ long-range or LoRa communication technology, which uses chirp short spectrum to achieve high sensitivity, low power and range by configuring bandwidth and spread factor. So unlike classical detection and deep learning approaches that only perform classification, our approach to IoT discovery reimagines signals as objects that can be localized in time and frequency using object detection. So the highlighted LoRa transmission exhibits a distinct time frequency visualization that actually fits our object detection paradigm. So our goal is to develop a robust, scalable system on resource-limited platforms. For this reason, we chose the You Only Look Once, or YOLO algorithm, due to its leading state-of-the-art inference speed, accuracy, and scalability. So to train our system, we developed a simulation pipeline by first collecting blank RF backgrounds at various frequency bands, and signals were digitally simulated and inserted into these waveforms. And because LoRa has high resistance to in-band interference, we allow the signals to be overlaid on top or behind pre-existing transmissions. And for each training batch, we randomly apply image augmentations to simulate realistic channel effects. And here's a real-time playback of 5 seconds using never-before-seen devices in a new multipath environment. And we can see that the receiver sensitivity translates to dramatic changes in contrast. And this approach can be applied to other IoT signals as well, such as Bluetooth, Wi-Fi, and Zigbee. Finally, here's a summary of our map results. Over-the-air tests were done over 2 miles away, and we were able to achieve real-time performance at over 81% map at image size of 288. So in conclusion, we've presented a robust lightweight system for IoT discovery in the RF domain using the YOLO object detection algorithm, and through careful analysis of the problem space and extensive collection, simulation, and image augmentation, our detection system has learned generalizable representations of IoT signal objects. And that's it. Thanks.
Good evening, everybody. So I will try to present a work on behalf of some of my colleagues who couldn't join today. So I will try my best, but so basically this work is about like one-shot object detection. So for modern object detector, there are basically two major streams, which have their own like speed and accuracy like trade-off. The one-stage detector is faster and has more potential to be applied for real-time application, but is also rather not very accurate. So here we investigate the cause for this ineffectiveness and try to find some solution. So the two-stage detector conducts its pipeline in a coarse-to-fine manner, while the one-stage detector predict directly the detection from a single image in an end-to-end manner. So the lack of a proposed and atom mechanism raised two main issues. The first issue is the inferior training samples from the lack of proposed mechanism. Modern detectors mine training samples based on IOU between default boxes and ground truth boxes. Regarding this, the two-stage detector provides the prediction module with rich training samples by proposing boxes that better match ground truth than initial boxes that is manually set. Meanwhile, the one-stage detector has a high dependency on initial box configuration of its quality of training samples. Thus, it will be ill-configured the initial box. The training samples can be extremely low or unbalanced during training. The second issue of receptive field mismatch for prediction module comes from the lack of atom mechanism. The two-stage detector can attend to accurate object feature for its detection by pooling layer, such as ROI align. Meanwhile, the one-stage detector lacks this attention function due to its fixed receptive field of prediction module, regardless of actual localization of object in an image. To resolve aforementioned issues, we propose a novel prediction module. It conducts the proposed atom mechanism, which is missed in most one-stage detector in an efficient manner. For the proposed mechanism, it adjusts the initial boxes to fit well with target boxes to reduce the gap between box distribution. And it also increased the diversity of training sample by limiting center displacement in its box regression. For the Atom mechanism, it modulates sampling points of convolution filter to get accurate object feature. Also, it is done in a non-parametric manner without adding any parameter overhead. Ooh, I'm very late here. So basically, they present very nice results. I think I can try to decipher a bit that in the poster, so you're very welcome to join at poster number 40. But basically, the idea is that they try to analyze the limitation of one-shot detector and to find some solution for this. So you're very welcome to visit the poster. Thank you.
Hi, I'm Jiang Hao from UCSD. My topic is LBP NAND, which is a convolutional free method. We are working on model reduction here. I list some state-of-the-art result, but we propose LBP NAND can achieve thousands of the compression rate here. Here is an overview of our method. It's a convolutional free method, but we can compare it with a convolution layer. As you can see, we replace some parts. I can explain this at our poster. Okay, people before us have already invented LBP, but when they use it, they just use fixed shape. The sampling shape is fixed, but we just turn it into learnable. Okay, here is LBP operation we use. There are 4 steps. First, we need to sample the pixel strength from the learnable apertures. Then we perform the comparison with the pixel, with the pivot pixel, and we allocate the result to a bit array, and then we move to the next position. Okay, if there are multiple channels, then we will perform the same LBP operation on those channels. And we use a random projection to fuse them together to get a single pixel for the output feature map so that we can avoid the addition. We want to avoid convolution and addition. Okay, how to change it? To use a convex optimization method, we need to turn everything into differentiable. Now we borrow the same idea from straight-through estimator, which is to use a hyperbolic tangent function. And then we apply the calculus chain rule to get the gradient with regard to the position, sampling position. Of course, it can work, but best method to understand how it works is to go through the optical flow theory. I will explain those equations at our poster. Please come to us if you are interested in this part. Sorry, so okay. Yeah, I can explain this. Okay, and we have implemented several FPGA accelerators. As you can see here, the model size is in kilobytes level, and if we're talking about the energy efficiency, is 61.3 times better than a Tesla K40. It's kind of impressive, right? Okay, that's pretty much I want to talk. And thank you. Please come to our poster for the result.
Hi, I am Prevendra from IIT Kanpur, and I'm going to present my work on filter pruning to get compressed model. And most of the work on filter pruning follow a common pipeline. In first step, they identify important filters, unimportant filters, and they prune some unimportant filters. And after pruning, they fine-tune the model, and then iteratively repeat this procedure. But all these methods suffer from one problem, like redundancy also exists in the compressed model. So in this work, we are doing redundancy-based filter pruning. And for redundancy, we are using correlation to measure the redundancy. So at a particular layer, we have, let's say, n number of convolutional filter. So we can get NC2 pairs. So we can create NC2 pairs, and we can measure redundancy for these pairs. So let's assume some pairs are strongly correlated. Let's assume pair let's assume redundancy is correlation is 60%, and if I prune one of filter from that pair, then we may lose some non-complementary information. So instead of pruning at that time, we are regularizing strongly correlated pairs to get highly correlated filter pairs. And at that time, we can prune one of filters, because these two filters, they belong to the same pair and they are highly correlated, and these two filters are applied on the same input feature map. So we can think the output feature maps also have some kind of redundancy. So we can prune one filter from each such pairs. So so this is our approach. We are selecting some highly correlated filter pairs, and we are optimizing these selected pairs. And after optimizing, we are discarding one filter from each pairs, and then we are fine-tuning and iteratively repeating this same procedure. And these are our results for ResNet 50 architecture on CIFAR 10, and these are our results for ResNet 50 on ImageNet dataset. And we have state-of-art results as compared to previous methods, which are based on filter importance-based methods. And these are our practical speed-up on CPU and GPU. On CPU, we have practical speed-up close to theoretical claimed speed-up. And on GPU, speed-up depends on base size. Like for a small base size, it is lower. So practical speed-up depends on machines, it depends on architecture, it depends on number of cores. Thank you.
Hi everyone, my name is Chun-Han, and today I would like to present our paper, 360 indoor total learning real-world objects in 360 indoor rectangular images. And with the growing amount of data, there is an increasing interest in computer vision to dig into 360 visual recognition. However, significant distortion of rectangular images is a crucial problem. In addition, lack of a suitable dataset makes it hard to evaluate the approach. Hence, in this work, we collect the first object detection and classification dataset on 360 domain. Our dataset consists 37 categories, 300 rectangular indoor images, and about 90,000 bounding field of views. For category selection, we consider the original categories defined in COCO dataset. We manually remove the categories having small sizes and add some common categories in the indoor scene. Overall, we have 37 categories selected for annotation. And we use bounding field of views as annotation in our 360 indoor dataset. Bounding field of views is defined by viewpoint, height, and weight. Since conventional bounding boxes label tool is no longer suitable for labeling 360 images, we designed annotation tool which can select the viewpoints and adjust the height and weight. To handle boundary objects, we extend the boundary using curricular padding. Below is the dataset statistics. We split the dataset into testing and training and testing with 70% and 30% respectively. Experiments indicate that all three detectors trained on our dataset significantly outperform detectors trained on COCO dataset. And we utilize mean average precision as the evaluation method. And the mean average precision overlap denotes that we only evaluate on the overlap categories between COCO and our dataset to calculate performance. More experiment results are provided in our paper and poster. And in the future, we aim at developing dedicated object detectors, overcome image distortion, and some new generation tasks such as image synthesis, image inpainting by using this dataset. Okay, thank you for your attention, and welcome visit our project website and discuss more detail with me during the process section.
Good evening, everyone. I'm Yi-Ting from USC. I'm going to present our new paper on non-expensive continual learning. Continual learning is similar to human learning. It retains and uses knowledge learned from the past to help future task learning. If we naively fine-tune a model for every new task we encounter, we may experience catastrophic forgetting on the old tasks. So the main drawbacks for the existing methods are forgetting, limited model capacity, and the decrease of the model efficiency. So we proposed our solution named REC to address each of these issues. One of the representative previous work then selectively retrains parts of its network and dynamically expands the network by adding more neurons, while REC expands the network through network transformation-based AutoML framework, and then compresses the model back to its original size. Comparing with the previous work in this area, REC is appealing because it has no memory growth, uses no exemplars from the past data, and expands the model capacity when it's necessary, and it will also leverage the AutoML. We propose a new regularization term using L21 norm and the sparsity inducing norm to prevent forgetting about the early tasks or learning about the new task. We formulate the model expansion part as a neural architecture search problem. For each time we encounter the new task, we first search for the best child network with net to deeper or net to wider operators in the controller, and incurring our novel regularization term in the trainer. Then we compress the network back to its original model size through knowledge distillation. We conducted the experiments on 4 tiny image classification benchmarks across the different domains. REC, denoting the cyan curve in all figures, demonstrates significantly higher average per task accuracy and a low forgetting effect on the early task than previous work. The same performance gain can also be observed in the real-world dataset like CUB200 as well. Finally, our model managed to achieve the highest accuracy with minimum model size. Please visit our poster at number 44 for more details. Thank you.
Hello, everyone. I'm Sarah Beery. I'm a PhD candidate at Caltech, and I'm going to be talking about some work that I did in conjunction with Microsoft AI for Earth. So the title of the paper is Synthetic Examples Improve Generalization for Rare Classes, and it's pretty much what it says on the tin. We were looking around early last year at all of the vast improvements in data synthesis that was happening, both through things like GANs, but also just these really high-powered, near-photorealistic graphics engines. And we were kind of curious whether these improvements would actually translate to real-world performance gain. So that's a performance gain in a system that wasn't sort of like a manufactured ImageNet style data set. So we're looking at the low shot problem that's kind of innate to natural world systems. So you have this long-tail distribution of classes, and sometimes the things that you care the most about are classes that are very low, represented very, very rarely. So things that show up a lot in species identification are things like endangered species. And so what we tried to do is we tackled this specifically in camera trap data. So camera traps are these static cameras that are placed out in the wild to monitor animal populations and behavior. And in these cameras, this low shot problem becomes even more of an issue. Because if you think of it as, okay, you have a rare class and that's showing up at one camera, then if it doesn't show up in another camera, even if you get 40 images from one camera, generalizing to a new camera is incredibly difficult. And so we decided to create sort of different types of data synthesis, and these are some combination of actual real imagery with these really high-powered graphics engines, and we wanted to use these to explore what the actual trade-offs were on real-world performance for rare species. So what we did is we took these four different things and we systematically varied both the number of simulated images considered, some axes of variability, so we would control for things like lighting or pose to look at how much improvement in performance you got from these different types of variability you had during synthesis. And then we also looked at actually the type of synthetic data. So where were you actually getting the most bang for your buck? Was it really worth it to develop a whole system that would synthesize data, or were there solutions that were sort of maybe more naive but got you almost all the way there? And what the biggest takeaways were that, yeah, using synthetic data for a rare species, we were able to decrease the error by 50%. So this is a big deal. But also, we really did see sort of a saturation point. So as you're increasing the amount of synthetic data, and this can be seen in the plot on the top left, there's kind of this point where you just start to learn a biased classifier. Yeah, so come talk to me at my poster if you're interested.
Cycle-consistent adversarial networks for zero-shot learning from natural language. Aiming to recognize instances of unseen classes, zero-shot learning is proposed to solve the data scarcity problem for those classes based on their semantic information. Recently, there are many generative models proposed to synthesize visual samples for unseen classes from semantic information to further perform supervised classification. The current challenges for those classes are the domain shift problem, the mode collapse, and the denoising ability for natural language. Here, we propose a cycle architecture with GANs to mitigate these issues. The objective function includes two minimax loss functions from GAN and the cycle consistency loss. The forward GAN firstly denoise the TF ideal features of the natural language input, and then synthesize the realistic and discriminative visual features. The inverse GAN takes the generated visual features to reconstruct denoised text features. The cycle consistency loss is further applied to regularize the forward GAN to uncover the semantics from the noisy TF ideal features. With the synthesized visual samples, zero-shot learning is converted into a supervised classification problem. We conduct our experiments on two datasets, CUB and NAB, to demonstrate the effectiveness of our proposed approach. And we outperform other state-of-the-art methods by a large margin. We also show the t-SNE visualization of synthesized visual features. It can be seen that the features are inter- and intra-class discriminative. Thanks for listening. If you have any questions regarding to this work, please feel free to contact me.
Hi, I am going to present my paper Accuracy Booster, and in this paper we are increasing the model accuracy without significantly increasing model parameters and computation. And there are lots of methods to increase the model accuracy, such as increasing more layers to a network. For example, in case of ResNet, ResNet 101 has better accuracy than ResNet 50 because it has approximately doubles layer than ResNet 50. And other method is just increase the number of filters per layer. For example, in case of wide ResNet, you can where they increase the number of filters and they are getting good accuracy than ResNet. But all these method increases number of parameters and computationally significantly. So in this, we are increasing model accuracy without significantly increasing computations and number of parameters. And for this work, we are using some attention mechanism, like we are calibrating feature maps, like we are giving more attention to highly informative features and suppressing spurious or less important features. So for that, this is our proposed approach where we have first applied global average pooling, then we applied depth-wise 1x1 convolutional filter, then Bayes normalization, and then sigmoid operator to get recalibration weights. And these recalibration weights are getting multiplied with input feature map to get recalibrated output feature maps. So in this recalibrated output feature maps, informative features are highlighted and less informative or spurious features are separated. So by doing this, we are increasing the model accuracy. And in this AB is our work, and you can see in this table, we have introduced only C extra parameters, whereas other approaches introduce 2C square by R and CBOM introduce less than 2C square by R. And these are our results on ImageNet dataset. And you can see in this table, we are just adding 0.01 million extra parameters, and we are getting accuracy close to ResNet 152. And similarly, in case of flops, and as you can see also in this table, we are adding, in case of ShuffleNet, we are adding only 0.02 million extra parameters, and we are getting much better accuracy as compared to ShuffleNet and the previous state-of-art approach. And also in inference time, our method does not increase inference time. For example, this AC method increases significant inference time, but our inference time is close to baseline. Thank you.
Hello everyone, my name is Barış, and I will present our work on generating positive bounding boxes for balanced training of object detection. Here we see the conventional training pipeline of a two-stage object detector. After the region proposal network generates regions of interest, that is basically bounding boxes for positive object locations, detection network is trained on these proposals. In this work, we aim to avoid the limited ROI source of region proposal network and use the bounding boxes generated by our positive region of interest PROI generator to train the detection network. In order to devise such a generator, a low-level procedure is required to generate a bounding box with the desired intersection over union value. So we propose a bounding box generator that is able to generate the green bounding box in the slide given, the blue bounding box, and the desired IO threshold. Then using our bounding box generator as a subroutine, given ground truths and desired distribution requirements, positive ROI generator generates a set of proposals to analyze and train the detector. Our positive ROI generator is able to generate a set of proposals with different classes, IO, and spatial distributions. We can train a detection network with different ROI distributions and observe its effects. The histograms show different ROI sources with different IO distributions. Some of our key findings are, among these distributions, uniform IO distribution for ROIs performs better, and training the detection network with the foreground class balance distribution also performs better. Based on our analysis, we propose online foreground balance sampling to sample among positives during conventional training of the detector by considering the number of examples for each class. Finally, we show that the existing detectors can use our positive ROI generator. Our method can train the network better, especially for larger IOs, by providing more ROIs. For example, we achieve around 10% AP improvement on the Pascal dataset when the network is trained for IO equal to 0.8. In conclusion, we showed that the detection network can be trained proposal sources other than region proposal network, and we proposed improvements based on our observations. You can check the code from the provided link. If you are interested in this work, visit our poster for more information. Thank you.
Okay, good evening, everyone. So this is Wenxue from University of Kansas. I'm pleased to present this work for my group mates Wenxue. This work is about towards learning affine environment representations via data-efficient CNNs. So we know that the CNNs are vulnerable to spatial transformation and takes a large data set for training. So in order to improve the robustness of the CNNs, we introduced a rotation invariant regularizer, and which would significantly improve the data efficiency and as well as the generalization and the robustness of the model. So the first contribution of this work is the multi-scale max-out block, which uses the 3x3 filters as the approximation for different sizes of filters. And this pixel level max-out is based on a multi-scale feature map, and it creates some sort of escape connections for pooling in the network. The second contribution is the regularization. This regularizing filter shape as a rotation invariant is reasonably designed, as the picture shows. And for the results, the proposed method is evaluated on 4 datasets. The datasets reflects different degree of spatial transformation. So the difficulty is different according to different datasets. And the model is compared to baselines that use different strategies to improve the robustness to spatial transformation. So such as in order to increase the robustness to rotation, the rod equalnet rotates the filter during the training to aggregate the information in multiple predefined directions, while the harmonics network regularizes the filters to be in a predefined shape. And we provide the comparisons across different models trained on different data set. And our method achieves the best performance on both the full data set and the few sample data set with 10 images, just a 10 image per class. The few sample data set contains randomly selected certain number of samples per class. And our model produces reasonably good performance while reducing the number of training samples, just as the solid right line shows in the figures. Here, these figures show the comparison with others using different numbers of parameters. We reduced the numbers of our parameter number by channel-wise shrinking. And we can see our model achieves competitive results with other models. And finally, we can find that the training and testing time of our model can be decreased in this way. Okay, so thanks so much about this work.
Hello, my name is Cody, and I'm from Texas State University. I'm going to be talking about pruning. Pruning falls into the broad category of compression and acceleration, and it's become very popular recently as we try to put these powerful models in the hands of mobile devices and edge devices. But there's still fundamental questions that remain unanswered. Like, we refer to the field as compression, but how do you know that the model that you prune has the same internal representations, the same decision-making policies as the model you start with? And if you're able to remove 90% of the weights from your model and retain accuracy, why did you need all the weights in the beginning? And additionally, once you find these sparse structures through pruning, do they actually have any value in of themselves? Do they encode the behavior of the model, or are they just useless? So the first thing we started to look at was finding a similarity measure that we could use and calculate it across all of the images in a data set. And so what we do is we take the similarity layer-wise compared to our dense models. And if you look at the distributions, as you increase the sparsity of the models, the similarity to the original models decreases, and sometimes kind of drastically. So it appears that the models that you have are not the same. Additionally, if we look at models with initialized sparsity, we have both a model that was pruned and reinitialized and trained from scratch, as well as a randomly initialized sparse model. And we see that there is actually not a very large difference between that and doing single-shot pruning without the many iterations. In fact, sometimes they perform better than traditional pruning. So it seems that maybe you don't need all of this capacity to begin with, and you can accelerate your pipelines. So what about the sparse structures? Well, it turns out that our reinitialized structures are no more similar to our original networks than randomly sparse structures that are trained. And you can see that the similarities have decreased dramatically from 85% as the median to like 50%. And also, the models with the random initialized sparsity seem to perform no worse than the ones with the learned structure. So these sparsity patterns seem to have almost no value. So it seems to be the weights and the actual connections, not the sparsity, that matters. So when we discuss pruning, we have to be very careful when we talk about compression, and we need to be considering more what effect this has on our models. Additionally, models can be trained with some amount of sparsity. If you're looking at compressing models, you can start there without doing as many iterations. And it seems the structures alone don't have any value. So thank you.
Hello everyone, I'm Samir, and today I'll be presenting on behalf of my colleague Ali, who was unable to attend. And the title of the paper is Transductive Zero-Shot Learning for 3D Point Cloud Classification. So the goal of the paper is zero-shot 3D object recognition. So the main challenge we faced was the embedding space quality is much higher in image-based than point cloud, because image-based pre-trained models such as ResNet use deeper networks trained on millions of images, whereas point cloud-based models such as PointNet use shallower networks trained on only a few thousand of point clouds. So you can see the difference between visual feature quality of image embedding space and the point cloud embedding space on actually four image data sets. So it is quite obvious that the quality of image embedding space is much higher than the point cloud one. So our approach has, what we do is we propose transductive zero-shot learning method using a novel triplet loss that is employed in an unsupervised learning manner. So there are a couple of benefits in our approach. The proposed method applies to unlabeled data such as interclass distance are minimized. And our proposed method is also applicable. Wow. So the contributions are, we extend and adapt transductive zero-shot learning and generalized zero-shot learning to 3D point cloud classification for the first time. And we also develop a novel triplet loss that takes advantage of unlabeled test data applicable to both 3D point cloud data and 2D images. And we also perform extensive experiments on state-of-the-art 3D data sets. So you can see the overall proposed method here. Sorry, he didn't provide me any notes on this. So you can see the difference of the inductive and transductive methods on this slide. The unsupervised triplet loss, which is shown here, has two main parts, the positive and the negative anchors. They are found for zero-shot learning and generalized zero-shot learning settings. So here you can see the performance of our method in zero-shot learning settings. And as you can see, we get this state-of-the-art results. And the generalized zero-shot learning accuracy of well-known 3D data sets are shown here. We obtain state-of-the-art results here too. So in this slide, we have shown our proposed method is also used on zero-shot learning on 2D data sets as well. We have reported the zero-shot learning and generalized zero-shot learning performance on 2D data sets. Thank you for your attention.
Today, I'm going to introduce our paper, Wide Hidden Expansion Layer for Deep Convolutional Neural Networks. We know increasing nonlinearity might produce a better network performance. One way is to design more powerful activation function, and the other is to increase the number of activation functions as more as possible. Our work belongs to the second one. Well, increase the number of activation functions comes with the network's depth increase, which is followed by the parameter computation and the memory consumption increase. To solve those problems, we designed a novel structure, Wide Hidden Expansion Layer, WHI layer. Each neuron in the hidden layer is sparsely connected with arbitrary 2 input channels and 1 corresponding output channel. One activation function appends each hidden neuron, In this manner, the number of activation functions is aligned with the number of hidden neurons. The number of hidden neurons is proportional to the square of the number of input channels. Therefore, our weight layer also can generate a large number of activation functions. In the weight layer, due to the sparse connection, only 4 parameters involved in the 3-MAC operation for each hidden neuron. If the input has C channels, we split the input channels into groups with group length G and generate CG hidden neurons in total. If group length is 16 and the number of the input channel is 256, weight layer only takes 1 out of 48 the complexity of the 3x3 convolutional layer. If we directly implement the weight layer, the memory consumption will grow with the number of hidden neurons. Thanks to the sparse connection in our weight layer, after splitting the input channel into a group, we can fit out the computation into GPU shared memory and compute the intermediate result on the fly. We evaluate our method on different network architectures on ImageNet dataset. In this table, we can see that our method outperforms counterpart models by up to 1.7% with input size 224 by 224. Our method outperforms original methods with up to 2% higher accuracy with less than 2% complexity increase for input size 150 by 150. We also made a sim depth comparison and replaced our weight layer with low-cost depth-wise layer. We can see that sim depth increase from depth-wise layer only results in trivial performance increase, while ours can contribute to 2% performance increase. We also compare our methods with other non-linearity increasing methods. Obviously, our methods can boost the performance higher than others. At last, we also evaluate our method on object detection task. In both COCO and Pascal VOC datasets, our method can boost more than 1% higher mean MAP compared to the baseline model.
Hello everyone, today I want to introduce you to Theodore, a synthetic omnidirectional top-view indoor dataset for deep transfer learning. My name is Roman and this is a collaborative work with Tobias and Gangov, both from Technical University of Chemnitz in Germany. Application fields are technical assistance systems for ambient assisted living or video surveillance. But first, a short recap. The related work can be divided in 2 classes. Existing datasets, here namely Bomni, HDA and fisheye dataset, and AI agents, for example Home. That is a multi-model environment for household activities, which is designed for learning-specific tasks and not able to directly generate images with labels. Let us assume we want to detect objects in fisheye images. We need to generalize models for these tasks. Current available datasets have lack of labeled classes and irregular distribution of classes to implicitly model the fisheye distortion. Our contribution can be described as follows. With a rendering engine here, Unity 3D, we create realistic images and corresponding labels of various indoor scenes in 14 classes. The camera is following a Lissajous curve for reaching a complex harmonic motion and different viewing angles with respect to the object. We create different 3D indoor living environments with highly variable textures as SMPL person models and various lighting conditions. The omnidirectional distortion is modeled by implication. We use 4 single perspective cameras and create a cube map for half hemispheric view that leads to a field of view of 180 degrees. With this work, we close the gap to unequally distributed bounding box locations, as you can see on the left-hand side. For this, we visualize the camera trajectory over the whole dataset and the distribution of bounding box centers in X and Y. On the right-hand side, the dataset class balance is considered. Results. Our object detection baseline contains of 3 state-of-the-art object detectors trained on COCO. Here, evaluation was done on HDA, Bomni, and own annotated data. For person class, we reach an AP of 0.8 on HDA and 0.99 on our dataset with SSD. For semantic segmentation, we evaluate on 2 architectures, SecNet and PSPNet. This was done on 6 classes with a class IOU of 0.67 for person and a mean IOU of 0.36 on own annotated data. Let's come to a conclusion. Theodore consists of 100,000 rendered images and labels of diversified indoor scenarios with human characters based on SMPL model. We create instant segmentation masks of 14 classes and bounding boxes for 6 classes. Our future work will concentrate on creation of omnidirectional depth, 3D skeletons, and optical flow. The data is publicly available through the shown QR code. Thanks a lot and feel invited to poster at location 53.
Hello everyone, this is Mohammad Farhadi. I'm from Active Perception Group at Arizona State University. Today I would present TKD, Temporal Knowledge Distillation for Active Perception. So these days, for reaching good accuracy, you need to run deep and deep models. You need to have so many parameters. And this creates a latency. The question is how we can reduce this latency while we are maintaining the accuracy. Let's take a look at the real-world scenarios. In the real-world scenarios, there is temporal relation between the frames. So we can take use of this temporal knowledge to improve the latency. What I mean by temporal knowledge, if this is the domain of the images that we need to learn, our DeepL model can learn most of it because we want to reach to the best accuracy. But do I need to know all of this domain? No. I can, at the real time, I need to know a specific region, a specific knowledge of this deeper model, which is moving. So if I found a way to a shallower model move around the deeper model knowledge, I can use for most of the time that shallower model for object detection and reduce the latency. So here you can see the method we are using. The input frames coming to the shallower model. Here you can see the structure of the shallower model that we have used. And we have a mechanism to detect whether we have a transition in the environment or not. If we have a transition, this is the time that we call a deeper or oracle model to run, and we are using this knowledge to update the shallower model and transit it to the new environment. Here you can see the result that we got. We are almost maintaining the accuracy. We have used YOLO V3 as the baseline, but it can apply to any model. We have maintained the accuracy while we are reducing the latency. I know you are exhausted. I'm also exhausted, so I have prepared a real-world demo for you. At the top, you can see our model and the Oracle model result. And you can see that the results are the same. And the bottom, you can see the shallower model without knowledge distillation. That graph shows the distance of Oracle model and the TKD, which is our model, at the inference time. And this is from my favorite TV3 office. I think you would also have to watch it. It's really interesting. So we would present a real-world demo, and also we would describe more specifically on the result that we got. At the poster session, I will be happy to see you there. Have a good day.
I'm here to present our work on shape-constrained network for eye segmentation in the wild. The problem we are to address in this work is to accurately segment eye regions, including sclera and iris, from in-the-wild facial images. This can have a variety of applications, including gaze analysis and attention estimation. As we are the first to study this problem in unconstrained environment, we first set out to create a dataset which includes nearly 9,000 eye patches taken from around 4,500 faces. The faces were taken from Helen 300W and other in-the-wild facial image datasets. We provide ground truth in terms of both control points coordinates and pixel-level segmentation masks. The dataset is freely available at our website. More than half of the eye patches in our dataset are at a resolution lower than 70 pixels, and hence are quite blurry and challenging to segment. Also, between 15 and 20% of the images are captured at a non-frontal pose or include occlusions. Here are some further examples from our dataset. Although semantic segmentation has been studied extensively, state-of-the-art method did not perform well on the eye segmentation task, especially when the images are blurry and thus does not give enough details or strong edges. To address this problem, we proposed the shape-constrained network. The intuition is that the shape of eyes is highly regular, therefore we can learn a shape prior to regularize the output of the base segmentation model. thus to give more accurate results on low-quality input images. In our work, the shape model takes the form of a VAE gun, which is trained on the ground truth segmentation mask separately. Once the shape model is trained, we use it to provide additional losses during the training of the base segmentation network. Specifically, in addition to the traditional IOU loss, the shape regularizer further gives a latent loss and a discriminator loss. The latent loss encourages the base segmentation model to produce results that have a similar shape code as that of the ground truth, and the discriminator loss promotes the model to give output that looks realistic in general. Experiment results on our dataset shows that our proposed method achieved higher IOU accuracy than state-of-the-art methods in both semantic segmentation and landmark localization. It is also faster than most deep methods. This is because the shape regularizer is only used during training and thus does not incur any additional computational workload at inference time. From the results shown here, we can see that our method gives much better segmentation masks for blurry input, thus leading to better accuracy. More details, including ablation study and cross-resolution test, can be found in our paper.